Hello, in this video I will be teaching you all about free body diagrams. A free body diagram is a drawing that we use to show the vector forces acting upon an object. You may be wondering, what's a force? A force is any push or pull that is acting upon an object. There are also a few special names for commonly used forces. Weight is the effect of gravity on an object. Weight is represented by mg, which is the mass of the object, times the acceleration due to gravity. This is an example of a free body diagram with weight as a force. The next force is normal force. Normal force, represented by n, is a force that acts perpendicular to the contact between any two surfaces. In this example, with the box sitting on the ground, the normal force is acting perpendicular, straight up, from the box and the ground. In the second example, with the box resting on the wall, the normal force acts towards the left, once again, perpendicular from the contact. Next, we have tension. Tension, represented by T, is any pulling force from a rope or string. We also have friction. Friction, represented by F(r), is a force that acts parallel to when two surfaces slide past each other. In this example, the box is sliding towards the right, which causes friction towards the left, parallel to the contact between the ground and the box. Next, we have a special kind of friction, drag. Drag, represented by D, is any friction force from a fluid, such as air, water, oil, and syrup. Next, we have lift, L. Lift is an upward force generated from a fluid flowing over a wing-like structure. And finally, we have thrust. Thrust is a force that is generated by rockets, propellers, and jet engines. Now, you may be wondering, why are we going to be using free body diagrams? Free body diagrams are very important because they help you organize the problem and clearly show the forces acting upon the objects and the directions they are in. If you do not use a free body diagram, the later physics problems will be extremely difficult, next to impossible to solve. The best way to learn how to do free body diagrams is through lots and lots of examples. So for this video, I am going to be walking through 5 or 6 examples to help show you what making a free body diagram is all about. Our first example, we will have a man pushing a crate of mass m with a force F across the ground. We're going to assume there is no friction or drag on the box. Our first step will be to draw the box in which all the forces are acting upon. Next, we need to set our coordinate axes. Setting this is extremely important for solving the rest of a physics problem. For this example, we are going to use a standard axes with up being positive y and towards the right being positive x. Next, we need to determine all the forces acting upon the object. In this example, we have gravity, the man pushing the box, and normal force. Now, since we know gravity always acts down, we can draw in gravity acting down on the box. Next, since there's contact between the ground and the box, we can draw normal force acting perpendicular to the contact, straight up. And the last force we have to draw is the man pushing the box. In the drawing given to us, we had the man pushing the box towards the right, so we just add in his force pushing the box towards the right. And that's our first free body diagram done. Now you can see we have all the forces and the directions in which they act. For our next example, we have Paratrooper Joe falling from the sky after he's jumped out of his airplane. We're going to draw the free body diagram for him while he's halfway down towards the ground. So once again, our first step is to draw the object. We're just going to use a box because it's simpler that way. Next, our coordinate axes. Once again, we're just going to use standard axes. Next, determine the forces acting upon Paratrooper Joe. We have gravity, and since he's falling through the sky, there's going to be drag. We know gravity always acts down, so we can just draw gravity acting down towards the Earth. Next, since drag is a friction force, we can draw the drag acting up as Paratrooper Joe is moving down past the air. Easy, right? For our next example, we're going to try a slightly different problem. In this example, Tarzan is swinging a rope across the jungle. At a certain point in time, his rope makes an angle theta with the branch it's connected to. So once again, for this problem, we are going to draw a box for Tarzan, label our coordinate axes. Once again, we're going to use standard axes, and list the forces that are acting upon Tarzan. In this case, tension and gravity. Gravity we can easily label as gravity acts down towards the Earth on Tarzan. Tension is more difficult. Since Tarzan is in mid-swing, we have to draw the tension towards the ceiling where it's attached. However, for doing the rest of the problem, we can't actually use tension at this angle. So, we need to be able to separate out tension into its horizontal and vertical components. In order to do this, we're going to use the angle given to us of Tarzan's rope swing and a little bit of trigonometry to reduce the components to a vertical t sine theta and a horizontal t cosine theta. Now that we have the force broken up into components, we can continue on with the rest of the problem. For our next example, we have a ball suspended from the ceiling by two ropes, one connected at an angle theta to the ceiling and another connected horizontally to the wall. This example is very similar to the last one. Only difference is that this one is connected to the wall as well, so we have an additional force. To start, we're going to draw our ball and label our coordinate axes. For this problem, we're once again going to use a standard coordinate axes. Next, we need to figure out all the forces acting upon the ball. In this problem, we have tension 1 connecting the ball to the ceiling, tension 2 connecting the ball to the wall, and gravity, mg. Once again, mg for gravity is simply acting straight down. Next, since tension 2 is simply horizontally connected to the wall, we can easily just draw that towards the left. And similarly, tension 1 is connected at an angle to the ceiling. Just like the last example, we can't use tension 1 in its current state, and we have to break it up into its components. Once again, using some geometry and trigonometry, we can determine that T1 in the y direction is T1 sine theta, and T1 in the x direction is T1 cosine theta. And with that, we're done with our free body diagram and are ready to move on to the rest of the problem. And now we're going to move on to our last example. For this example, we have a box resting on a ramp. There's also no friction or drag, so the only forces acting upon this box are gravity and normal force. Once again, we're going to start off by drawing our box. In this case, we're going to draw our box slanted since it is slanted in the problem. Our second step is the coordinate axes. For this problem, since the box is tilted, we are actually going to tilt our coordinate axes with the box, making towards the upper left positive y and towards the upper right positive x. These coordinate axes will be used later in the problems and are extremely useful, so make sure to tilt them in the right direction. Next, we are going to label the forces that we know are acting on the box, normal force and gravity. Once again, gravity will act upon the box straight down towards the bottom. Now remember, normal force is always perpendicular to the contact between two objects, so the normal force will be acting in the positive y direction towards the upper left. Once again, in this problem, we need to break up the forces. But we're not going to break up the normal force. Normal force is already in our coordinate axes. Instead, we need to break up gravity. Once again, we're going to be using the trigonometry with theta to break up gravity into its components. The negative x component will be mg sine theta, while the negative y component will be mg cosine theta. And once more, we're done with